Hey everyone, and welcome. Today, we are going to decode a really powerful mathematical language, one that lets us measure our world in ways that honestly feel, well, impossible. We're talking about trigonometry. And believe it or not, it all starts with a simple question.
Seriously, think about that for a second. How would you actually do it? It's not like you can just run a giant tape measure up the side of Mount Everest or stretch one all the way to the moon. This is exactly the kind of impossible problem that stumped some of the most brilliant minds for centuries, until they found this incredibly elegant solution that was hiding in plain sight the whole time.
And that solution is trigonometry. The name itself is a huge clue. It comes from these two ancient Greek words, trigonon, which means triangle, and metron, meaning measure. So it's literally the science of measuring triangles. And that right there is the secret to measuring all those unreachable distances. Okay, so how does this ancient tool actually help us measure the modern world? Well, it all comes down to one simple, absolutely perfect shape.
Meet our hero, the right triangle. Yep, this is it. It's just a triangle that has one perfect 90-degree angle, like the corner of a book or a tile on the floor. And this simple shape holds a secret, a kind of hidden language that connects its angles to its sides.
So, to crack this secret code, we've got to learn the vocabulary first. And trust me, it's way simpler than you might think. It all starts with just giving the sides some special names. In any right triangle you'll ever see, the longest side, that's the one directly across from that 90-degree corner, is always called the hypotenuse. The other two sides get their names based on which angle we're looking from. The side directly across from our angle, we call that the opposite. And the side that's right next to our angle, that's the adjacent. That's it. Opposite, adjacent, hypotenuse, that's our vocabulary.
Now, what about the angles themselves? What even is an angle? Well, it's just a way to measure rotation. Just picture one line staying put and another line rotating away from it, like the hand of a clock. The amount of that turn, that's the angle. Usually we measure that rotation in degrees, where a full, complete circle is 360 degrees. Now, there are other units like radians, and they become super important later on in physics and higher math. But for what we're doing today, let's just stick with degrees. It's the one we all know. All right, so we've got our triangle, we know the names of the sides, and we can measure the angles. Now, here comes the magic. This is the core idea of all of trigonometry. This right here is the absolute key, the big aha moment. If you have a right triangle with, let's say, a 30-degree angle, the ratio of its opposite side to its hypotenuse will always be the exact same number. It doesn't matter if that triangle is tiny enough to fit on your fingertip or if it's miles wide. That angle locks in the relationship between the sides. It's because all right triangles with that same angle are similar. They're just bigger or smaller copies of each other. This is the whole game right here. So mathematicians gave these super useful fixed ratios some special names: sine, cosine, and tangent. The sine is just the ratio of the opposite side divided by the hypotenuse. The cosine is the adjacent side over the hypotenuse, and the tangent is the opposite side over the adjacent. These three ratios are our main toolkit. So how on earth are you supposed to remember all that? Well, with one of the most famous little memory tricks in all of math, SO, CA, TOA. Sine is opposite over hypotenuse, SO. Cosine is adjacent over hypotenuse, CA. And tangent is opposite over adjacent, TOA. SO, CA, TOA. Just say it a few times. That little phrase is your key to unlocking everything. Okay, theory's down, we've got our tools, we've got SOHCAHTOA burned into our brains. Now let's actually put it to work and solve a real problem. So let's circle back to that idea of measuring something you just can't reach. Instead of a whole mountain, let's start with something a bit smaller, like a flagpole. We want to know how tall it is, but we don't have a ladder anywhere near long enough. So how can our new friend trigonometry help us out?
It's actually a super simple three-step process. First, you just measure your distance from the bottom of the flagpole. That's something you can measure, right along the ground. From our angle's perspective, this is the adjacent side. Second, you use a simple tool, even your phone can do this, to measure the angle from where you're standing all the way up to the top of the pole. Now you have an angle. You're looking for the height of the pole, which is the opposite side. So, which one of our ratios uses opposite and adjacent? TOA, tangent. You plug in the numbers, do a quick calculation, and bam, you've found the height, all without ever leaving the ground. Pretty cool, right?
And this whole idea of using angles to find distances, it's not just for flagpoles.
Not even close. It is, well, it's everywhere.
And this brings us to two really key terms you'll hear all the time in the real world. That angle you measured looking up at the flagpole, that's called the angle of elevation. Now, if you were standing on top of that flagpole looking down at yourself on the ground, that would be the angle of depression. These two ideas are absolutely fundamental for surveyors, pilots, engineers, you name it. And the applications, oh man, they are absolutely endless. Astronomers use this stuff to calculate the distance to stars and planets. It's the backbone of navigation systems like GPS that get you where you're going. Engineers and architects couldn't build stable bridges or incredible skyscrapers without it. And yeah, believe it or not, video game designers use trigonometry every single day to make characters move, simulate physics, and render those amazing 3D worlds.
So what's the big takeaway here? It's that this secret language that started as a way for ancient thinkers to map the heavens has become this totally essential tool that literally builds and shapes our modern world. From ancient stargazers to today's game developers, the language of triangles is truly universal. It really makes you wonder, right? If a simple shape like the triangle holds such a powerful code for understanding the universe, what other universal languages are still out there, hiding in the patterns all around us, just waiting for us to discover them?